Okay, so this is the work through of the molecular structure 2, which is essentially just drawing a whole bunch of Lewis structures and then looking at them and interpreting them in terms of the electronic geometry and thus the shape and hence the polarity. So I'm just going to go through at various levels of speed as we do all of this. So hopefully it will answer any questions that might be left unanswered by just simply looking at the answers. So CO2, very straightforward Lewis structure, one of the ones that one does as a big test most of the time. You've got carbon that wants 4 bonds, oxygens that want 2 bonds each and have 2 lone pairs, so thus that is the Lewis structure. For assigning the VSEPR considerations, all one cares about is the central atom. In this case there is but one central atom, the carbon. And then you first of all count groups of electrons around the carbon. Well, each line is 2 electrons, so you'd say, oh, there's 4 pairs of electrons. Absolutely, but that's not what I asked. We asked for groups. The 4 electrons in this double bond are one group. The 4 electrons in this double bond are another group, because these 4 electrons have to be between the carbon and the left-hand oxygen. These 4 have to be between the carbon and the right-hand oxygen. Yes, I'm violating Heisenberg's uncertainty and everything there, but you get the main gist. So 2 groups of electrons around the carbon. 2 groups of electrons arrange themselves so they are as far apart from each other as possible, which is obviously for 2 groups of electrons a linear arrangement. Now that's as far as the carbon is concerned. It's got 2 groups of electrons around it. It is linear. As far as we're concerned though, we don't see lone pairs on the central atom. We just see bonding pairs and the effect of the lone pairs. So that's the question for going from electron geometry to shape. Yep, there's 2 groups of electrons, but are they bonding? Are they lone pairs? What? In this case, 2 bonding, 0 lone pairs, which means that we see that exact electron geometry as the shape, linear, 180 degrees. And this molecule is the classic example of a molecule that has polar bonds, because of course oxygen much more electronegative than carbon, but those polar bonds cancel out, so the molecule itself is non-polar. Moving to another one that unsuspecting naive students say, oh, it's going to be the same. You've got a central atom with 2 oxygens. Not so fast, right? You can't apply common sense, because common sense says that both of those atoms, both being in group 6, chalcogens, group 16 if you want to use the fancy modern terminology, they both want 2 electrons, thus 2 bonds, and the only way you can have 3 atoms with 2 bonds each is an ugly looking triangle that you don't see outside of carbon chemistry. So we have to apply the method. As 18 valence electrons, each atom has 6. Sulfur is the less electronegative, thus it will go in the middle, and so our first attempt at a structure will be this one here, in which you have 2 single bonds between the sulfur and each oxygen, and then each atom has enough extra lone pairs to take them up to 8. Trouble with that is there are 20 dots. 20 is a lovely number, but in this case it's horrible because it's not 18. So we have to reduce the number of dots. And if you think back to our molecular structure 1 discussion where we learned the method, or the method I use anyway, for assigning weird Lewis structures, in order to reduce the number of dots by 2, we take 2 atoms that are already bonded because we don't want to mess with the connectivity. We remove 2 lone pair-ish dots from each, so we've erased 4 electrons, and we add in an extra bond, so we're just replacing those 4 with 2 electrons, thus a net reduction in 2. So there we are. I could have picked the left-hand oxygen as I did. I could have picked the right-hand oxygen as I did. Thus, in a topic that was an extension in molecular structures 1, each of those bonds is actually equivalent, because it could be a double, it could be a single. That's an example of resonance that, like I said, it's a nice little extension topic in molecular structures 1. So anyway, looking at that, sulfur is the interesting central atom. How many groups of electrons around the sulfur? Well, double bond is 1 group, a single bond is 1 group, a lone pair is 1 group, thus 3 groups of electrons. For 3 groups of electrons to arrange themselves as far apart as possible, they adopt a trigonal planar geometry. So as far as the sulfur is concerned, it's trigonal planar. As far as we're concerned, we can't see that lone pair, we just see the effect of it. So there are two bonds, one lone pair, which means that it is the shape that you get when you take a trigonal planar and remove one of the legs from it, as with this picture here. That looks kind of like a crustacean of some kind, little piggy eyes, and then either the long whiskers for a lobster or a crustacean or whatever. But anyway, so that is a bent structure. The angle should be 120 degrees, but because lone pairs are more repulsive than bonding groups, the lone pair pushes them away a little bit, so the angle gets a bit smaller, so slightly less than 120, 118 degrees or so would be my prediction. Now, any time that you have polar bonds attached to a central atom and a lone pair, that lone pair is going to distort the geometry. And unless the lone pairs cancel out, the molecule is going to be polar. Okay, so one page that illustrates quite a few interesting things. You had to use both approaches to drawing Lewis structures, common sense, and then the method with capital T, capital M. And you saw one in which the electron geometry and shape were the same because there were no lone pairs on the central atom, and one in which the presence of a lone pair means that the electron geometry is not the shape. The shape has to take into account the fact you do not see one of the bits of the electron geometry.